Hello and welcome. In this video I want to show with the help of an example how we can dimension a rotor blade using the blade element theory. For the dimensioning I have chosen an example wind energy plant which is the Enercon E48. This plant has a nominal power of 800 kilowatts. It has a rotor radius of 24 meters, a nominal wind speed of 12 meters per second, and the number of rotor blades is 3. The tip speed velocity is 78 meters per second. And I assume that the lift force coefficient Ca is 1.2 and the drag force coefficient is 0.02. In case of all calculations, the rotor is divided into blade elements with the thickness dr of 1 meter. First of all, we calculate the optimal pitch angle theta for each blade element. Therefore, we first calculate the axial velocity Va. This velocity has the same number for each blade element and is 2/3 of the wind velocity. Thus, in our case, it is 8 meters per second. And afterwards, the tip speed ratio is calculated. This is the tip speed divided by the wind speed, and in our example it is 6.5. After that, some calculations for the element at the tip with a radius of 24 meters are carried out. For this element, the resulting velocity Vr is calculated in the beginning. And this is the square root of u to the power of 2 and Va to the power of 2. So in our case, it is 78.41 meters per second. And afterwards, we calculate the angle delta, thus the sum of angle of attack and pitch angle. And this angle is calculated by the arcus cosinus of u divided by Vr. The result is 0.1 in radian measure, thus 5.86 degrees. For this blade element, we have to assume a value for the angle theta, which is our constructive parameter. We assume that this angle at this blade element is 0 degrees. And after that, we can calculate the angle of attack alpha. The angle alpha is the total angle delta minus the pitch angle theta, thus it is also 5.86 degrees. And afterwards, the same calculation is carried out for the next blade element, which is 1 meter closer to the rotor blade center and thus has a radius of 23 meters. In the beginning, we calculate the circumferential velocity u according to the equation tip speed ratio multiplied with the radius of the blade element and divided by the total rotor radius multiplied with the wind velocity. And in our case, we get a result of 74.75 meters per second. After that, we calculate the resulting velocity Vr. It is calculated by the square root of u to the power of 2 and Va to the power of 2 and is 75.18 meters per second in our example. Afterwards, the sum of the angle of attack and the pitch angle is calculated. It is again the arcus cosinus of u divided by Vr. In our case, this leads to 0.11 in radian measure, thus 6.11 degrees. And the requirement in order to reach equal flow compared to the previous element is that the angle of attack alpha is the same compared to the element before. So in our example, it has to be 5.86 degrees again. The pitch angle theta, the constructive parameter, can be calculated again by subtracting the angle of attack alpha from the total angle delta. And thus, for this blade element, the pitch angle theta is 0.25 degrees. The same calculation has to be carried out for all further elements to the center of the rotor blade. For all further elements, the assumption that the angle of attack alpha is the same at all blade elements has to be valid. After that, I will calculate the optimal blade depth Tb for our example. In the beginning, the calculation is carried out at the blade tip at a rotor radius of 24 meters. All the values of the equation are given, so the optimal blade depth at this element is 0.88 meters. And after that, this calculation is carried out for the next blade element at a radius of 23 meters. And when inserting the given values, we reach an optimal blade depth of 0.91 meters for this element. The same calculation has to be carried out for all further blade elements until the center of the rotor. In this graph here, you can see the optimal blade depth Tb and the pitch angle θ depending on the blade radius r. The blade depth is shown on the left y-axis and the pitch angle is shown on the right y-axis. On the x-axis, the radius 0 corresponds to the center of the rotor blade and the radius 24 meters corresponds to the blade tip. It is visible that the blade depth and the pitch angle decrease with increasing rotor radius. After that, I want to show an example where I calculate the relevant forces at each blade element. In the beginning, we calculate the lift force Fa. First of all, we calculate the lift force at the blade tip, thus at the radius r of 24 meters. And the lift force is calculated according to the here shown formula as explained in a previous video. All values are given or we have calculated them in a previous step. So it is important that the corresponding values for this blade element are taken for the blade depth Tb and the velocity Vr. With these values, the result for the lift force is 3.85 kN for this blade element with a thickness of 1 meter. The same calculation must be carried out for all further elements to the center of the blade. Afterwards, the drag force is calculated. This is also calculated at the blade tip in the beginning. And when the given and already calculated values are taken into account, the result of the drag force at this blade element is 0.06 kN. And the same calculation has to be carried out for all further elements until the center of the blades. Afterwards, the tangential force Ft is calculated. In the beginning, this force is also calculated for the first element at the rotor tip at a radius of 24 meters. And all values for this blade element are given from the previous calculations. We get a result of 0.33 kN for this blade element. And this calculation is again carried out for all further elements until the center of the blade. And finally, we calculate the axial velocity Fax. This velocity is first calculated for the blade element at the blade tip, having a radius of 24 meters. And we know this formula from a previous video. The values are given from previous calculations. Thus, the axial velocity for this blade element is 3.83 kN. And this calculation again is carried out for all further elements until the center of the blade. In this picture, the calculated forces are shown depending on the rotor radius. A rotor radius of 0 at the x-axis corresponds to the center of the rotor blade, and the radius of 24 meters corresponds to the blade tip. You can see that the lift force and the axial force have the highest values, and the drag force has the lowest value as wanted. The lift force and the axial force increase with increasing rotor radius. And in the next video, we will see why most wind turbines have just 3 rotor blades. Thank you very much.